Hello, my name is Nady Carmona Aguilar, and in the following video, I will be talking about the work entitled Optical Characterization of 2A and 2C Organic Compounds. First of all, I would like to thank the audience for their interest and attention to the presentation of this poster. The topics we will cover in the presentation are the main objective, a brief introduction, the methodology used, and finally a discussion of the results obtained and the conclusions reached. The main objective of this study is to demonstrate that compounds 2A and 2C have potential for applications in optoelectronic devices and sensors. To this end, an optical characterization was performed for both compounds using two spectroscopic techniques: the ultraviolet visible UVVS technique and the photoluminescence technique. Well, it is no secret that organic compounds with the ability to absorb and transmit light in a controlled manner have aroused the interest of the scientific community in recent decades. This is due to their great potential for applications in optoelectronic devices and advanced sensors, as they combine flexibility and low cost. In this context, the organic compounds named 2A and 2C were subjected to optical characterization using the techniques described above. With the spectra obtained, their band gaps were calculated using the TOC method and their luminescent emissions. Next, we can see compounds 2A and 2C on the screen in figures 1 and 2. Now, why are techniques such as UV-vis absorption spectroscopy and photoluminescence so relevant in the optical characterization of materials? The answer is that they allow us to understand their electronic structure, forbidden bands, and the efficiency with which these materials emit light after excitation. While absorption spectra reveal the nature of pi asterisk transitions, photoluminescence analysis provides information about radioactive and non-radiative processes. Knowledge of these processes is crucial in the development of OLEDs, organic photodetectors, optical sensors, and biomedical devices. As compounds 2C and 2A were presented as finely powdered solids, it was necessary to dissolve them in dimethyl sulfoxide, a solvent. This solvent does not interact with the compounds. Optical characterization of compounds 2C and 2A was carried out using two techniques: photoluminescence and UVVS spectroscopy. Specific details are shown below. For the UVVS technique, the sample dissolved in DMSO was placed in a lambda 35 Perkin-Elmer spectrometer. The spectrum was obtained within a wavelength range of 200 nanometers to 1,100 nanometers. For the photoluminescence technique, the sample carrier was adjusted to 30 degrees inside the nanolog modular spectrofluorometer, with scans performed in the following wavelength intervals. Compound 2C, 300 nanometers to 600 nanometers. Compound 2A, 500 nanometers to 700 nanometers. Figures 3 and 4 show the devices used to perform each technique. The results obtained for each technique are shown in Figure 5. UVVS spectroscopic analysis is shown in figures 5A and 5C and revealed that in the ultraviolet visible region, 200 to 600 nanometers, both compounds exhibit intense absorption around 200 nanometers, which is attributable to pi asterisk type electronic transitions. This indicates a high electron density in the pi orbitals, which is favorable for photoinduced absorption processes. The forbidden bands were estimated by the TOC method from the abrupt drop in absorbance near 400 nanometers. Compound 2C has a band gap of approximately 3.1 eV, whereas 2A's is between 3.1 and 3.2 eV. In the near-infrared region, 600 to 1,100 nanometers, noticeable peaks were observed between 800 and 950 nanometers for both compounds, suggesting the existence of intermediate electronic states or structural defects. On the other hand, photoluminescence is shown in figures 5B and 5D, where we can observe that the maximum peaks were identified at 2.069 eV for 2C and 2.066 eV for 2A, which confirms radiative recombination within the near-visible range. The proximity of these values suggests that despite their structural differences, the presence of the methoxy group in 2C, their photoemitting behavior is similar. In conclusion, we can say that both compounds have optical properties compatible with semiconductor materials, with band gaps between 3.1 and 3.2 eV. In addition, The presence of intermediate electronic states evidenced in the NIR range could be exploited for specific applications, such as photoactivated sensors or long-range emitting materials. The photoluminescence curves show emission in the near-visible range, which reinforces their potential for optoelectronic technologies, such as OLEDs or chemical sensors. The differences in intensity and resolution between 2A and 2C suggest that substitution with methoxy groups influences the density of states and the overall optical response. Finally, these results open the door for future research aimed at modifying or functionalizing these compounds in order to fine-tune their optical behavior for specific devices.